So hi everyone. Can you hear me? Any like thumbs up or yes or no in the chat? Yes, it's recorded. Yeah. Okay, let's see. So yeah, good. So I'm Bibek. I'm a TF 161D, and today we are going to solve few problems. So about 6 problems. So these are like past exam problems, and the exam that you'll be writing on September 10th. The basic concepts in this exam will be like similar to what we'll solve today. So let's give another 1 minute for the students who want to like join. Let's wait 1 more minute and we can start. We have a good number of people. Yeah, 43.
Excuse me, you're on mute.
Oh, can you hear me? Sorry. Yeah, that's why. So the first problem that we'll be solving is the velocity versus time plot, like graph-based problem. So basically here you can see that train starts from rest, and the speed of the train increases, and it reaches maximum at some point, and it continues to go straight, like with a constant velocity in a straight path for some time, and it deaccelerates and comes to zero again. So how to solve this one? So the first question is that describe the problem. So what's happening over there? So let me draw the. Okay, let me put this over here. Let me zoom this in. So let me draw the graph again. So this is time, right? And this is your speed. So speed is the magnitude of the velocity. So we're not taking care of the direction right now. We just need the magnitude. So that's it. And the unit is meter per second. And it starts from 0 and goes to point A and goes to point B. And it's like this. So the time for it to reach from point 0 to A is like 62 seconds. From A to B is 50 seconds. And from B to C is 25 seconds. So we have 3 intervals. So number A. So when you want to describe the problem like this, so first it starts from rest. So you need to mention that. That's one point. And the other one is like from point O to A, the speed is going up with time. That means your velocity or the magnitude of the velocity is increasing. That means you're accelerating. So the train accelerates from O to A, right? And from A to B, it's moving with a constant velocity. So the acceleration is 0, so it's moving with constant velocity. Constant velocity from A to B. And lastly, it deaccelerates. The speed is decreasing with time. So your velocity will decrease eventually, and it comes to stop at this point. This point is C. So deaccelerates from B to C. So that's it. That's how you like describe problem like this. So let's go to like number B. So this one was easy. So let's go to B. So now it's asking for you to find the acceleration from O to A. So what's the acceleration from O to A? So it's given in the problem that the maximum velocity that the train reaches is 36 meters per second. So this is the maximum velocity or maximum speed, right? The magnitude, and that is 36 meters per second. So the velocity at point A is 36 meters per second. And the velocity, so initially, what was its velocity? So initially at O, its velocity was 0 meters per second because it was at rest. So since it's a problem involving time and speed, so it's a kinematics problem. So you need to use the equations of the motions. So if you want to find acceleration and you have velocity and time, so we also have the time, but we don't need the distance. If you don't need distance, but you need a formula that involves velocity, acceleration, and time, so you use this one. The final velocity is the initial velocity plus the acceleration times time. So here your final velocity is VA. So we are solving for this interval, O to A, this interval. And your initial velocity was 0 meter per second. So that's VO, plus the acceleration is what you need to find, and the time is it's 62 seconds, sorry. 62 seconds. So let me just write time for now. So it's a good habit to do the algebra first and plug in later on. So I'll just do the algebra. So OA is VA over time, right? So 36 meter per second divided by 62 seconds. That gives you about 0.58 meters per second square. So that's your acceleration OA. So I think this one was also not that hard. So let's go to the other problem. So for doing that, let me just drag this diagram down. Oh, sorry. It's very hard to scroll and take the diagram down. Okay. Okay, we're good. So we're here for number C. So it's asking for you to find the acceleration from B to C again. So it's like it's an acceleration problem. So you need to use the same formula again. So the acceleration BC will be final velocity minus the initial velocity, of course. So that's VC minus velocity at B divided by time. So I'm using the same formula. That's final velocity is initial velocity plus acceleration times time. So your final, so your velocity at point C is 0 because it comes to rest over here. So it's negative velocity B over time. So that's negative 36 meter per second. 0 minus at point B is same speed, like 36 meter per second. So meter per second divided by 25 seconds. So that gives you about negative 1.44 meter per second square. So that's your acceleration. And it makes sense that we are getting acceleration negative because we are deaccelerating, right? So our speed must decrease with time. That's what it says, the negative sign. So do you have any question till now? Anybody? So I guess that's a no.
Well, I was just wondering if you're going to post the answer key after we finish with the session.
Oh yeah, of course I will. Yeah, thank you.
Thank you.
So let's go to number D. Okay. So here you need to find the distance from A to B. So yeah, one of the hard thing about teaching online is, you can't share your full screen at one time. It's very hard. So let me drag this down. Okay. So we need to find the distance from A to B. So we know that the velocity, the train is moving with constant velocity from point A to point B. So that's velocity AB is 36 meters per second. And the time that the train takes to reach from point A to point B is 50 seconds. So the definition of like distance in terms of velocity is just like, the definition of velocity is distance traveled over time. So this gives you that the distance AB is velocity AB times time. So that is, so that is your velocity is 36 meters per second times your time, that's not 25, that's 50. So that's 50 times 50 seconds. So it's about 1800 meters. So that's your distance. So you can write in kilometers. XAB. And lastly, so I think we have reached to one of the important section of the problem, which asks for total distance traveled and average velocity. So we'll need this plot. Sorry. It's very hard to do this thing. Let me try once again. Slow. Okay. So lastly, you're asked the total distance traveled. So that's the distance that you travel from point O to point C. So let me just tell you what's the regular way of doing it, because there are basically two ways you can find distance. One is the easier one, and one is the lengthy one. So the longer version, you can find the distance x OA, and you can find x AV, and find the distance BC. So you use the equation of kinematics. There's distance is equals the initial velocity, times time plus half of AG squared. So you use the formula and you find it, because you have the acceleration for all these three intervals. For this interval, the acceleration will be 0. And for other two intervals, you have already found the acceleration, and you have the time, so that you can find three distance. You can add them, and you can find the total distance. That's the long way. But I want to do the shorter, the quicker version, and that's to find the area under the curve. So if you have any curve like this, and the curve is let's say there's pressure versus volume, then the area of the curve is gives you the product of the basically you can do area of under the curve can give for this case it gives energy. You don't need to know this, it's from thermodynamics. So let me just take an example of so if you take an area under the curve here, that means that you're just doing finding the distance, because area is just the product of two lengths, right? So you are multiplying speed with time, and the unit of speed is meter per second. The unit of time is seconds. So you can see that we will get a distance. That is, we will get a total distance if you can find the area under the curve. So let's find the area under the curve. So that is total distance is equals the area under the speed versus time curve. So that is the area of triangle OA. This point is x and this point is y, x, and the area of triangle BYC, and this triangle, and the area of the rectangle ABYX. So this will give you the total distance. So how do you find the area of the triangle? If it's a right triangle like this, and if this is a base, this is a height, then you just do half base times height. That will give you the area. So for this triangle, that's half. So what's your base? Your base is like, you know, if this is angle, this is your base. That's 62 seconds. 62 seconds times what's your height? That's 36 meter per second. And similarly, you can find the area of the other triangle. Half times 25 seconds times 36 meter per second. And lastly, the area of the rectangle, that's, you know, this height is 36 meter per second and the length is like 50 seconds. So it's just length times the breadth. So it's 36 meter per second times the 50, what was it? 50 seconds. So if you do it, do the calculation, you'll get about 3366 meters. That's the total distance, x total. Okay. So lastly, we need to find in number E, that is the average velocity. Represent it by V average like this. So average velocity is the total distance over the total time. So you have already found the total distance in our previous section. So that's 3366 meters divided by what's the other total time? That's just 62 plus 50 plus 25 seconds. So you get about 25 meters per second. So that's your V average. So that's it. That's how you solve number one. So if you have any question, you can ask me right now. So a quick revision. We started from the rest. We accelerated and the train was moving with constant velocity from A to B, and there was the acceleration. We found the acceleration from point O to A. We found acceleration at the end. That's a point from B to C. We found the total distance. We found the distance from A to B, and we found the total distance. And remember that area under the curve, it will come again in some other problems that we will be solving today. So what the area under the curve gives is always the product of the y-axis and the x-axis. So in this case, there's speed times the time. So that's the distance. So sometimes there might be some other, you know, physical variables. So you'll get something totally different. So that's fine. And lastly, we found the average velocity. So if there is no problem, so I'm moving to number 2. I hope you are opening the presentation file and looking at the problem while I'm solving it. So let's look at the second problem. So there's a projectile problem, number 2. So there is a football player that kicked a ball, and the ball moved in a projectile motion, and we need to do some calculation based on it. So I guess you have already learned about the projectile, so let's solve this one. Okay. So the first part of the problem asks us about like which component is the first graph and which component of the velocity is the second graph. So we have two plots over there, right? So it's the time in the x-axis and the velocity in the y-axis. We have time and velocity, but we don't know which velocity is, which component of the velocity this first one is. So it starts like this, and the other one is like this. So it starts from 14.7 meter per second, and it reaches like 0. The velocity reaches 0 and goes to negative, so something like negative 14.7 meter per second. And this starts from 25 meter per second, and it's constant throughout the projectile, throughout the trajectory of the projectile. So if you look at a projectile, so it's like this. So you throw something with at an angle, and it goes like this. This is theta. This is your v, 0x. That's the initial velocity. So if you resolve it, if it's v naught, there's v naught cos theta, and the y component of the velocity is v naught sine of theta, right? So the force acting on the projectile is the acceleration due to gravity. That's downwards. So the acceleration, since the acceleration due to gravity is towards negative y, if you consider this to be positive y, this to be positive x, your acceleration is due to gravity is towards like the center of the earth. So that's contributing to slow down your projectile towards y direction. But the g has no effect over the x direction. That's why the horizontal component of your projectile always remains constant. So that means this has to be, so the x component of the velocity, right? Because throughout the entire motion of the projectile, the velocity is constant. This component is constant. That means it has to be the x component. And if you look at the y component of the velocity that the projectile has, so at first it starts with like v naught sine theta, but after some times, since the acceleration due to gravity is the only force acting, the magnitude of the velocity decreases, and it reaches 0 at the maximum height of the projectile. And then as soon as it starts moving from the maximum height, the y component again it starts to increase, but in the opposite direction. So you have in your final, when the ball strikes the ground, the final velocity is like this, and your y component is towards the negative y, and your x component is equal to the v naught x, because it's always the same. It will always cover the equal distance in equal time. So that's the fundamental thing about the projectile. So the first problem asks you to draw the projectile and level the diagram. So this is what the level diagram looks like, and this is the maximum height that the projectile reaches. And so let's do number B. Okay, so in number B, you are asked to find the maximum height that the projectile reaches in. So what is h? So you have the initial velocities, and since the height travel is towards the y-axis, we don't need to care about the x-axis velocity. So the initial y-axis velocity is v0y is v0 sine theta, and that's equals to 14.7 meter per second. Because if you look at the plot here, the projectile started, this is the y component, right? So it started from 14.7 meter per second as a y component, and for x it was 25 meter per second. So if you level here, this has to be 14.7 meter per second, and this has to be 25 meter per second. So we have like 14.7 meters per second as the initial velocity towards the y, and it reached to zero, like a maximum height with zero velocity. So your final velocity for the half of the time travel is zero. So you know the acceleration ay is minus g, that's the acceleration due to gravity. Why minus? Because g is towards negative while you're moving towards positive y, so you need to take negative g. And the h is unknown, so you need to use like one of the like most important equation in the kinematics, that's the final velocity square is the initial velocity square plus 2 times acceleration. So it's towards the y, so I'll write y, and the distance h. So that's the equation of motion that you'll be using here. Since your final velocity is zero, so this part will be zero. So, and yeah, you know, this is negative g. So if you write s correctly, then it's negative v0y over 2 times negative g, right? And so the negatives and negative cancel out. So I think there has to be squared. So it's 14.7 meter per second squared divided by 2 times the 9.8 meter per second square. So it's about 11.025 meter. So that's your maximum height gained by the projectile. So any question till now? You can ask me. So I guess we can move forward.
Yeah, one question real quick. The other like delta y equation where it's delta y equals 1/2 times time plus. You know which one I'm talking about?
Yeah.
Yes, that won't work too.
So you mean the other equation? So we have basically 3 equations of motion, right? So one is final velocity is initial velocity plus acceleration times time, right? And the other one is the same one that we just used. I'll just write u square as the initial velocity plus 2 times acceleration times the distance. And the other one is the x is initial velocity times time and half acceleration times. So these are the 3 equations of motion you have to deal with in the kinematics. But here we have like the distance as unknown and the time is also unknown. So if you want to use the like this equation, you need to find the time at first, and then you can basically do you can use this one.
Okay, thank you.
But but this equation can't give you the h because it's not involving distance. So either you have to use this one or this one. So you need to find time so that you can find h like this.
I have a question with the first graph.
Okay.
It gives you like the time intervals too, and so it's at 1.5.
Oh, yeah.
Velocity hits 0. So can't we still do 1?
Yeah, you can use the other equation in that case. Yeah, I forgot that. Yeah, the time, there's also time axis here, so you can use you can just read the time from the graph and use the time and find the distance using this equation. Okay.
Hey, Bibek, I have one more question. So for that one, I used one of the equations for the vertically launched projectiles. I used delta y equals VIY t plus 1/2 AT squared.
Oh yeah, it's the last one. This one.
Yeah.
Right. Yeah.
Which one? Sorry.
Yeah, this one, the third one. This one.
Yeah. Yeah, and for some reason, the first time I did this, I got that answer, but the second time, I got 49.5 meters that time. Because I multiplied the velocity times the time. And for
so
the time
I think the probable mistake is you took the total time, like from here to here. So that's the
total time.
Because you need to take the t half because you are going from here to here. So you're just taking the time from here to here. So the projectile coming from here to here. So that's that
would only be 1.5 seconds, right?
Yeah, it won't be this would give you a wrong answer. So you have to take the half time,
Right.
half the time of the slot.
Okay, cool. Thank
So
you.
that, okay. So is there any other questions? Can we move forward?
I have a question.
Uh-huh.
So when we have to show our work for the exam, as long as we get the right answer and we show our work and we use one of the equations,
Yeah.
or do we have to use a specific?
So it's totally fine if you use another equation and do your problem. We'll just look at the process. If the process looks fine, it's totally fine. You can do it, you know, at whatever you feel is comfortable. Yeah.
Okay, thank you.
Yeah. And always like when you are solving your exams, you need to label your diagrams properly and you need to write the units, you know. So if you notice me doing the problems, I'm using units even during while I'm doing my calculations. So it's easier, you know, you can cancel out. Even if you don't know the units, you can find the units by just doing algebra like this. So keep that in mind. So let's go to the next number. That's so one more thing. So we can do this thing graphically as well. So I did it using the equation of motion, right? The number V. So we can do it graphical. So if you look at the graph, the Y component graph, the first one, is the speed, that's the Y speed, right? Vy versus time graph. So if you find the area under the curve, because since we're going from here to here, that's the half of the total time of flight. So if you find this area under the curve, then you'll get the distance h is the area under the curve, curve from this time to this time. So that's about like this time is about 1.5 seconds, right? And we started from 0. So area of the under the curve is just half times. So this height is 14.7 meter per second times what's the time? That's 1.5 seconds. So if you do, you'll get about 11 meters. And that's also one of the easiest way to solve the problem. That's why I was saying like area under the curve is like very important technique to find, you know, some physical quantities when you're solving problems. So let's go to number C. And it's asking for you to, you know, it's asking you the maximum range or the range basically. So how do you find the range? So this is your projectile, right? It was launched with an initial velocity. It has x component. It has y component. Angle is theta. So the range is the distance from here to here. Or you can also say it length of the projectile. That's totally fine. So it's easier. So if you look at the second graph, the one involving the x component, so it's like this. It's 25 meter per second, and I think the time is about 3 seconds, right? Yeah, it's 3 seconds. So it's going up to 3 seconds from 0. So this is your Vx component. This is your time. This is your time, and this is your Vx. So it's always constant, 25 meter per second. So you have the velocity for this path. At each point you have the velocity, and you know the time interval that it takes from the projectile takes from to go from here to here. So that's 3 seconds. So you know velocity is distance over time, right? So the distance here is the range that you need to find, and the time is the total time. Let me write this capital T, and the velocity is v0x or vx, whatever you want to call it. So that's your range. R is velocity. That's times time. That's 25 meter per second times 3 seconds. So seconds and seconds do cancel out, and it's 75 meter. So that's your range. So I think it was not that hard. So if you have any question, you can ask me for this one. Okay, let's move on to number D then. So I think number D ask you to find the launch angle, right? Okay, so till now we haven't used launch angle and like any problems. So we just know we already know the x and the y component of the velocity. So how do you find the launch angle? So it's pretty. If you guys might have already guessed. If you look at here, I've already equated like v naught sine theta is 14.7 meters per second and v naught cos theta is equals to 25 meters per second. So just if you divided the two of them, you'll easily get the angle, launch angle. So your x component is v naught cosine of theta, that's 14.7 meters per second. And your y component is v naught sine theta. Oh, sorry, I think I wrote wrong. This one has to be 25. It has to be 14.7 meters per second. So now if you divide this two, there is let me call this one 1 and 2. If I divide 2 by 1, I'll get sine v0 sine theta v0 cos theta is 14.7 meters per second divided by 25 meters per second. So your units get cancelled, your velocities get cancelled, and you get tangent of theta is equals 14.7 over 25, and theta is tan, so inverse tan of 14.7 over 25. So this is about 30.5 degrees. So okay. So I think this one was also not that hard. If you have any question, you can ask me. So I guess that's it. Let's go to number E then. So it asked for you to find the final velocity as when the projectile hits the ground, right? So if the projectile was coming like this and finally it hits the ground, what's the final velocity just before it hits the ground? So this will be the final velocity, and it has both components. If you resolve it, you'll get like v final x, and this will be v final y. So we don't need this now since we already have the components. So in projectiles like this, since the problem is saying that we can neglect the air resistance, what happens is that your y component of the final velocity will be equal in magnitude with the initial y component of the velocity. That was over here, sorry. That was like over here when it launched. The v naught y was over here, right? So this length and this length of the vector will be equal, but the direction will be exactly opposite because it's going towards positive y here and it's coming towards negative y here. So the direction will be negative. So that's one thing. But if there was air resistance, it's not true. So let's not go into that because they won't ask you the problems involving air resistance. So, and the x component, that's this velocity, will be equals to the x component that the projectile had initially. So your final velocity v final is just used, like if it's a right angle triangle, you just use the Pythagorean theorem, or you can just use the vector addition. So whatever you feel comfortable. So it's a triangle, right? So this is v final x, and this is your v final y. You have 90 degree in between. So how do you find this length? So this is your final velocity. So it's just, okay, drop this one. V final E square is V final Y square plus V final X square. And your final velocity is, that is, since there's the square of negative v0y, so it's just v0y squared, the negative will be positive, but it's only direction, so you don't need to take negative. It's just you take the magnitude, square it, and vfx is v0x squared, so it will be equal to v initial, it's the magnitude, so it will be equal to the initial velocity's magnitude. But as you can see, the direction will be negative because it's going downwards. So the final velocity will be negative, negative of the initial velocity. That means it has same magnitude, but the direction is opposite. So you can see here as well. So your final velocity, the initial velocity is going in this direction, and your final velocity is going in this direction. So they are exactly going towards the opposite direction. So a lot of the students make a mistake in made mistake in this problem last time when I was grading. So they were like doing all the other calculations. So you don't need to do any other calculation. You just need to remember that the y component is equal to the initial y component, but in the opposite direction, and the x component remains constant throughout the motion. So the x component is always same. So if you go here, you can find that the vx will be equals to v naught x wherever you go. But vy changes, so vy decreases, reaches 0, and increases towards the negative direction. So I think that's it for this problem. Do you have any question?
Yeah.
Yeah.
Yeah. So I'm not really sure just when to use this method of finding velocity, because every time I come across, because I always make the mistake of using one of the kinematic equations to solve this.
Oh.
Right.
Yeah.
I mean,
okay.
always.
Okay. So so there are basically 3 kinematic equations. So you just need to make sure which one to use. If you are if you don't need time for your kinematic equation, suppose you are driving a car, you hit the brake, and you need to calculate the braking distance, then you don't need to use the first equation because it involves time, and you don't have the time. You just have it doesn't involve the distance. You need to calculate the distance. That means you have to either use this one or this one. But if you have time, go for this one. If you don't have time, you only have the acceleration and the velocity, go for the second one. So that's how you filter out which one to use,
All right.
So that's it. Do you still have any other questions? Anyone?
Yeah, I just have a real quick question. I did use one of the kinematic equations. I used the VF squared equals VI squared plus 2A S. And if you just make S 0, since the change in Y is 0 because it hits the ground, doesn't that whole thing just cancel out and you just get V squared equals V squared? So they're just the same.
Oh, so you mean when you start from here and you reach there? So
yeah.
So this is not displacement. So it's not a displacement. So displacement is the shortest distance between 2 points. So you start in the morning, you go to your office, you come back to your house. The displacement is 0 in that case. Yeah. But this equation, this S means this is distance. Yeah, your distance, displacement can be 0, but distance can be 0 when you go somewhere. So this distance is this range R.
Okay. But it worked though. I got the right answer.
Did you use the second equation?
Yeah, I did. But like I said, I just instead of using delta x, I used delta y. The formula sheet doesn't say s; it says delta x. So I just used delta y instead because you can use it for the x or y because they're independent.
Yeah.
And they just made the whole term 0. Is that okay or no? I shouldn't do that.
You mean like finding the maximum height while you're finding maximum height?
No, not finding maximum height. Just to find the what were we finding? It was to find the velocity of the ball right before it hits the ground.
I see. Oh
Yeah.
Yeah, in that case, yeah.
Oh, okay, awesome. Thank you.
Yeah.
As for that would just get you back to what you were saying, which was just VF squared equals the same magnitude as VI squared, just negative, right?
Yeah.
Okay, that makes sense.
I just used an equation for it.
But don't use your s equals to 0 in like when you are working with the x. I don't think it's a displacement. If it's displacement, yeah. But I think the formula is for distance. So if it's distance, even if you get right answer, they might not accept your answer.
Okay. Good to know.
Yeah.
For this problem, when you did in part, when you were trying to find the launch angle for part D, when you did sine over cosine to get tangent,
yeah.
Would you recommend knowing all of the other rules? Because I think, to be honest with you, when I took trig in high school, the only one that I remember is sine over cosine is tangent. I don't remember like cotangent and like all that.
Oh, you won't be asked any other trigonometry. You just need to remember these things.
Okay, basically just sine and cosine and then tangent.
Yeah, that's it.
Okay, and then did you give the magnitude for the final one there for E? The actual value itself. I may have missed that.
You don't need the value.
Oh, you don't need the value. Okay.
Yeah.
You just need to know that it's the same value as the initial.
Yeah. If you want to write the value, it's fine. But they are just testing you. If you know the final velocity will be negative of the initial velocity or not. They are just checking you. Okay.
Thank you.
Okay. So I think now we can move to number 3. And after number 3, we'll take a short break and come back again. So number 3, so this is also a projectile problem. So you have the launch angle, and I think you have, what else? Let me just read the problem. So this is number 3. So when jumping, you take off and at an angle, sorry, there was a typo, angle of 30 degrees. So there is a projectile that's launched at an angle of 30 degrees, and that lands back 0.6 seconds later. So you are given the total time of the flight. So let's solve this one. Okay. So you have a projectile, and so it has a launch angle, which we don't know right now. But what we know is the total time of flight, that is 0.6 seconds, right? And we know the launch angle, that's 30 degrees. So your x component is v naught of cosine 30, and your y component is v naught sine 30. And this is your range, the total distance range, and this is your height h. So I think the first part asks you, the number A asks you to find the y component of the velocity. So to find that, we can use is the equation of motion. So we'll use v final is equals v initial plus acceleration times time. So since we have time in our in our hand, like they have given us the total time. That's the time that it takes from go from here to here. So to reach the maximum height, the time is halved, right? So it takes 0.3 seconds to reach the maximum, and the rest of the time projectile takes like 0.3 seconds. So to reach the maximum height, so from here to here, so you have the initial velocity, that's the y velocity, and you know the y velocity Vy is 0. So if you only look at long y, so you don't need the x. So V final, that's Vy is, your initial is V0y plus acceleration ay times t half, right? So your final velocity is 0 at the maximum height. So your V0y is negative ay t half. So you know your ay is the acceleration due to gravity, that's towards the negative, going towards negative y. Since your motion is towards the positive, while the projectile, your motion is towards the positive, but your acceleration due to gravity is towards the negative. So you have to take negative g times t half. So this will give you g times t half, which is 9.8 meter per second squared, times your t half is 0.3 seconds. So that will give you 2.94 meter per second. Okay, now, do you have any questions till now? I think it's pretty much similar to what we did in our last problem. So for part B, yeah, you need to find the x component of the velocity, right? V naught x is what? So you already know V naught y, that's V0y is V0 sine angle of theta is 2.94 meter per second. And you know the launch angle is 30 degrees, right? So you have the theta, you have the Vy, so you can find the V0. So V0 is just the launch velocity is V0y divided by this sine angle of theta. That's 2.94 meter per second divided by sine angle of 30 degrees. So your launch velocity, the magnitude of the launch velocity is about 5.88 meter per second. But you need to find the x component. So you know that the x component of your velocity is the launch velocity times the cosine of the launch angle. That's 5.88 meter per second times cosine of 30. So that gives you 5.1 meter per second. So that's it. So it looks like a theta. So let's go to number C. I think.
What does the answer say? Does that say 5.9?
Yeah, 5.1. Well, did you get a different answer?
Oh no, I just couldn't read what number that was.
Yeah. I'll post this my notes as PDF at the end of the lecture. So yeah, just for the information. So the number C, or the part C, asks you to find the length of the jump. So don't get confused with the length of the jump. So it's range. So they're just changing the wording to. Okay, so the range is, you know that the x component of the velocity is same, at every point in your projectile. So it's always the same. So it's always, the projectile is always covering equal x distance at equal time interval. So your range is just the x velocity times the time of the flight, because you are calculating the distance from here to here. You need to take the time for the projectile to go from this point to this point. So that's 0.6 seconds. So your V0x is what you just found, 5.1 meter per second, and your time is 0.6 seconds. So that gives you 3 meter as the range. So now we come to the last part of the problem, and that's asking you to find the same thing like that the other problem was asking earlier. So it's asking you the final velocity. So it's also like a vertical projectile. You fire it with a launch angle and it comes and hits the ground with velocity. So you have X component, you have Y component. So sometimes you are asked to find the like the final like the angle with which it hits the ground. So you can either find this angle or this angle, doesn't matter, but you need to specify which angle you are calculating. So I've already told you how to calculate the final velocity. So I'm just writing the final velocity will be negative of the initial velocity. But you need to give reasoning in your exams. Just don't write directly that final velocity will be negative of the initial velocity. You need to provide some reasoning or some calculations if you want to. And to find the launch angle, so this is the right triangle, right angle triangle. So this is 90 degree, this angle. This is angle phi that you want to calculate. This is your x velocity, that's vfx, and the y is vfy. So if you you need to know this trigonometry as well. So if there is a right angle triangle, right, and this is launch angle theta, let's call this side as P, this side as maybe hypotenuse H, or this side as, I call it base, I call it perpendicular, and I call it the hypotenuse. You might call it differently. But so if you want to find the launch angle, and you only have, right now you only have this opposite of the angle, that's this, and you don't have the hypotenuse, so you have this. So if you use tan phi over here, tan phi will give you pfx over pfy. And if you do the inverse tan, you can find the launch angle, the angle with which the projectile strikes the ground. So sometimes they ask problem like this as well. So keep that in mind, how to calculate the launch angle. And you can also find this angle, let this angle be beta, and you'll be doing this similar kind of trigonometry, but you need to specify that this angle is the angle that the projectile makes with the ground, and this angle is the angle that the projectile, the final velocity, makes with the vertical line. So you need to specify that which angle you calculated. So we have done like 3 problems, and I have like 6 problems in the PowerPoint. So I'm giving you like 5 minutes break, so you can.
So what was the final answer for that last part?
So it's calculating, it's asking you the final velocity, right? The number 3, last part. Mm-hmm. So as I have already described you in number 2, that the final velocity will be like equal to the initial velocity. So final velocity by which the projectile hits the ground, right? It will be equal to the initial velocity.
So the final answer is just that?
Yeah. It's just this one, but you need to provide reasoning. And the reasoning you can give is like, you can either solve calculations like I did here in number 2, or you can just write that in wording.
Okay.
Okay, so let's take a break and come back like at 6:35, I guess. So it's 6:35. So let's solve another problem. So in this problem, boy is rolling a stone in a horizontal circle of radius 1.5. So he was like just rotating a ball or something, and the string broke, and now the ball flies like a horizontal projectile. So we have been asked like how to find the time, the time of flight, how to find the velocity the moment that the stone hits the ground. So let's see how to solve this problem. Okay. So let me draw this scenario over here. So suppose this was the person that was getting the string, and he was rotating the ball like this, the stone like this. Okay, and the string somehow broke. So this is the string, and it somehow broke, and there was like the stone came like a horizontal projectile, and now you need to find the range and stuff like that. So for the first part of question for us is you to find, like, draw a good diagram. So let us consider this to be our axis. This is y, this is x, and when the stone comes like this, and it goes and it hits the ground over here. So you have the y component of your velocity. That's 0 initially. So it's only going towards the x-axis, positive x. And you have like the x component of the velocity that's non-zero. So your v0x is non-zero. And you have the acceleration due to gravity that's acting downward. And you are given this height. Let us call this delta x. That's, or not delta x, no, delta y. That's 2 meters. And the range is given to you, and that's 10 meter. And it's been told that initially the length of the string for this uniformly rotating stone was 1.5 meter. So at first, after you draw the level diagram, at part B, you're asked to find the time of flight. So what is the time of flight that stone takes to come from here to here? So let's use the equation of motion. So you have the distance, that's delta y. You need to find the time of the flight. You know the acceleration, that's g. So which equation of motion do you use? So you use that equation of motion, which involves all these three. That is, delta y is v0y t plus half the expression ay t squared. So your initial vy was 0. As you can see here, the ball is only going towards the x at first, and due to the gravity, it starts the projectile motion. And the vy was 0 here, but the vy increases like this, and the vx is always constant, like in the case of the vertical projectile. Okay, so your vy was 0 initially. So you have the delta y, the magnitude of delta y, and you need to find the t. So that is t is delta y, 2 times delta y over ay square root. So that's 2 times, your delta y is 2 meter, and your g is, see, in this case we'll take the g as positive. So why is it positive? It's because last time the ball was when in the case of vertical projectile, the projectile was going up and g was acting downward. So in that case, we took negative g. But in this case, the projectile is going down and the g is also down. So they are in the same direction. So we'll be taking g as positive, because you can't have a negative inside the square root. That's an imaginary thing. So you do the square root, and the answer is 0.64 seconds. So do you have any question till now? So let's go to part C of the problem. So you're asked, what was your initial velocity, that's v0x towards the positive x direction when the projectile started? So you're given your delta x, right? You have the delta x, and you know the total time of flight is 0.6 seconds. Let me draw this. And so how do you, so you when you used to find the range, you used to use like delta x and time, but and you already, if you had like velocity, you could find the range. But in this case, it's asking you the exact opposite. You are given the range, and you need to find the velocity. So the range is 10 meters in this case. So that's your velocity is the distance over time, and your distance is 10 meters, and your time is 0.6 seconds, 64 seconds, I guess, 64 seconds. So this gives you 16 meters per second as your initial velocity towards x. So let's go to number D. Okay. So nobody asked you to find the acceleration with which the boy was like rotating this stone in this uniform circular motion. So this is a uniform circular motion question now. So in the uniform circular motion, what happens is your acceleration is always towards the center, and it's known as the centripetal acceleration. And at each point in the circle, you can draw the velocity. And the velocity vector is towards the tangent, but the speed will always remain the same, although the direction is changing. So that's why we call it uniform circular motion, because the velocity is always uniform at each point, but your direction, the direction of the velocity is changing. And at one point, if the string breaks loose, then it just starts to fly like a projectile. That's what we did in the first part, because it moves towards the tangent. So how to find a centripetal acceleration? So you have like a very famous formula that centripetal acceleration is the square of the velocity, the speed, divided by the radius. So in this case, our radius is 1.5 meter, it's given to us. And the velocity is, since when the string broke loose last time, we calculated v naught x was 16 meter per second. So, you know, the velocity by which the person was like rotating the stone was the x component of the velocity that we found here. So that's 16 meter per second square divided by 1.5 meter. So this gives you 170.6 meter per second square. So it's pretty high, about like 17 times g. So it's a very, very, very huge acceleration. So do you have any question? We're done with number D.
Yeah, I have a question.
Mm-hmm.
Would it be okay to find the centripetal acceleration using the unrounded version of the velocity?
Unrounded means?
Because yeah, like with more significant figures and then rounding it after.
It's fine. Like it's fine. Like if you find velocity differently, and so you got like not exactly to what I'm getting, right? Like you are getting somewhat different. Like after the decimal.
Yeah.
It's totally fine.
I
If
did.
values are near, it's fine.
Okay, because I did part D with the velocity as 15.6 as opposed to the 16, and ended up getting about 163.
Oh yeah, yeah. I just approximated it to be around 16. Yeah, to be exact, it will be about 15.6 or something like that. Yeah, that's even more near to the actual value. That's fine.
Okay, thank you.
Yeah. Any other questions? So let's go to number 5. Let me stop at number 5. So you have a car of mass 1200 kg that's traveling along a straight horizontal road at a speed of 20 meters per second. And so you suddenly press a brake. So you need to draw a free body diagram. You need to find the distance. You're given the acceleration and stuff like that. So it's a force related problem. So it involves in the Newton laws of motions. So you have a car that's traveling in a straight line. Okay. So the mass of the car is 1200 kilogram, and the initial velocity was 20 meters per second. And at some point after and if you hit the brake right here, at some point it will come to a stop. So you need to draw the free body diagram when it was skidding somewhere in between. So this is a car. So how do we draw free body diagram? So you have like, let us consider this to be the center of the car. So the acceleration due to gravity is towards the center of the earth, that's downwards. The mass of the car times the acceleration due to gravity, and the ground is here, so it will give it a normal force that's directly opposite to the weight force, that's the normal force. And let me draw this as a vector point because these things are vector. So you don't need to draw vectors, you can just write N and G. I like to do it vectorically. And when the brake is applied, there is friction in the wheel of the car. So the friction force or the net force is towards this side. F. I'll write it F friction. It's fine. If you write like any other force, it's just writing F or F8 is fine. And plus X. So there aren't any other forces. So a free body diagram is just a force diagram. You just mention all the forces that's acting on an object. So you cannot have two objects in one free body diagram. You need to draw separate free body diagrams. For if there are two bodies, they are separate bodies which have like forces acting on them. You need to draw a separate diagram.
I have a question.
Uh-huh.
You draw to the right of the free body diagram, like what does that say? It looks like it says like TN. Is that?
You mean this? It's positive X. Yeah. I'm writing it's positive X.
Oh, positive
X and it's positive Y. So I'm just writing the direction.
Thank you.
Okay. Yeah, sorry about that. Any other question? So yeah, that's the free body diagram. So we'll be doing another problem with free body diagram at the end of this session. So let's go to number B. So you're asked to ask the distance the car travels after like the brake was hit, and the braking distance basically. So the S represent the braking distance. The car was here and it came to stop over here. So you can do it. You know you need to calculate the distance, and you're given the acceleration. The acceleration is given as AX is -7 meter per second square. Why I'm taking negative is the brakes are in opposite direction to the motion. So always, if the acceleration is acting towards the opposite direction of the motion, like in the case of projectile, you take the negative, the acceleration as negative, because it's decreasing the velocity. Your initial velocity here was 20 meter per second. So at the time when the driver hit the brake, the velocity was 20 meter per second. And your final velocity, V final, is 0 because the car comes to a stop. So which equation of the motion do you use? You don't have time, you have the distance, you have the velocity, and you have the acceleration, and you need to find the distance. So you cannot use this equation, that is because you don't have the time. So this one won't work here. So you need to use this equation, acceleration times the distance. So your final velocity is 0, right? And the distance is, if you do the math right, square over 2a, and that is -20 meter per second square divided by 2 times -7 meter per second square. So this gives you the total distance of about 28.6 meter. So this is your braking distance. You can also solve this problem using work energy theorem. So if you know work energy theorem is work done is the change in kinetic energy. So work done is force times the distance, and your final kinetic energy minus the initial. So final kinetic energy is 0, and this is half the mass times the initial velocity square, and your force is mass times the acceleration, right? And that's -half mvi square. The acceleration is given, the mass is given, but the mass will cancel out, so you don't need the mass. So if you do the math, square over 2a. So this is also a simpler way to do the problem. So it's an alternative way to do the problem. Do you have any question till now? Okay. So let's go to part C of the problem. So now it's asking you to find the time it takes for the car to stop, like after the brake was applied. So it was the car, and it was going with initial velocity 20 meter per second, and the final velocity was 0, right? And what's the time? Time from here to here. So now you have the distance already. So you can use like basically any equation of motion, but the easiest one here will be, since we know the acceleration is -7 meter per second square. So my notations might be some, might vary, So this is, I was writing A. This was, I think I wrote V2 or something like that. Okay, just make sure that the notations are same. Oh, I was using the final. And so the easiest one will be the equation of motion involving velocity, acceleration, and the time. That's V final is V initial plus A times the time. Since your final velocity is 0, you can find T as -VI over A. So you're -20. Oh, I think the problem is quite, I think I read the problem wrong. So I think it's asking you when the car was in the middle of the road, like it was still skating, but
It changes the final velocity to be 12.
Yeah, so it hasn't stopped yet, so it's still moving, but the velocity now has dropped to 12 meters per second, right? And it will come to stop at some point, but not here. It might stop over here, but we need to calculate this time, not the total time. Sorry for that. So the time that the car takes to reach from this velocity to this velocity. So that means this final velocity is not 0. So it's 12 meters per second. So let me just erase that. And that gives you final velocity minus the initial velocity divided by the acceleration. So your final is 12 meters per second minus the 20 meters per second velocity divided by the negative 7 meters per second square. So 12 minus 20 is minus 8 over minus 7 is just 8 over 7. That gives you 1.14 second. So make sure that you don't get the time as negative. Time can't be negative. If that was possible, we will be traveling back in time. So that means you're doing something wrong with the algebra. So if you have any question, you can ask me right now. Okay, so last part of the problem where you are asked the distance, this distance. So we just calculated the time for the car to reach from 20 meters seconds to 12 meters per second. Now we need to calculate the distance. So we just need to use the different equation of motion. That is, you can use either this one, or you can also use the other one, the last one that the one with delta x. You can, because you already have the time, so you can use that one as well. So if you do the calculation, let me write this one as s prime, because it's not the total braking distance, otherwise my notation will overlap. Okay, so that is v final square minus the v initial square divided by 2 times ax. This is 12 meters per second square minus 20 meters per second square divided by 2 times negative 7 meters per second square. So if you do the calculation, you'll get this distance to be around 18.3 meters, and that's fine. You know, it's less than the braking distance. The braking distance was 28.6 meters, and we got now 18.3. Do you have any question? We are going to number 6 otherwise. So let's go to our last problem of this session. That is 1,000 kilograms roller coaster goes through many drops throughout its ride. In one particular drop, it goes down a 65 degrees incline plane with a starting velocity of 52 meters per second. So neglect the air resistance. So you need to draw the inclined plane and level the forces acting. That means you need to draw a free body diagram, and you need to, and we are also doing some other calculations. So problem number 6. Let me jump. Okay. So imagine this as your inclined plane for the problem, and let this angle be the theta. That's 65 for this case. And your, like, the car is starting from here and it goes to there, and somewhere in the middle. So let's draw a free body diagram. So your weight force is directly towards the center of the earth, that's always down. So that's mass times G, that's your weight force. And you have normal force. You have normal force. Since you are in the inclined plane, the normal force will be to this direction. And you can just resolve it back like this. Let's tell this direction, let us suppose this direction to be positive y, this direction to be positive x. So, and if you do the math, so if you look at here, in this triangle, this is a small triangle, this is a right triangle. So if this angle is theta, this will be 90 minus theta. And since this angle is 90 degree, this angle, this small portion will be theta. 90 minus 90 minus theta will give you theta. This small angle. This entire angle is 90. This is 90 minus theta. That means this will be theta like this. So if you resolve your weight towards the positive y, then you'll get your y component of the weight as mg cosine of theta, like we did in the projectile, just resolving this vector to this direction. So let me just erase this. So it will be something like this. So you have mg cosine of theta coming here, and you have the other component of this weight force. There's towards this side. There's mg sine angle of theta. So now we have resolved the weight. Let's solve the problem. So this was part A. We drew a free body diagram. Now we'll do part B, where we need to find the height of the plane. So that is this height h from here to here. And I think we're given this distance as well. Now let me write this distance to be s. So we need to find h. We have the time for which the car takes to come from point A to point B. That is 4.5 seconds. And the initial velocity at point A was 52 meters per second. So when the car was here, the velocity was 52 meters per second. And now first let's find this distance, so that since we already have the angle, we can use the trigonometry and find this height h. So to find the distance s, we need to use the equation of motion. So the equation of motion that we can use here is delta x is equals the initial velocity times plus the half axt squared. So your delta x is s here, and vi is 52 meters per second. Your time is given 4.5 seconds plus half. And what's the acceleration? So the most important part is finding the acceleration. Since your car is traveling down the inclined plane, and nothing other force except the weight is being acted on the car. So mg sine theta is the acceleration with which the gravity is dragging the car down. That is mass times ax. So your mass cancels, and your acceleration is g sine of theta. So it's always true for an inclined plane, the acceleration by which any object is pulled downward, the inclined plane is g sine theta. So the acceleration is independent of the mass. So the acceleration is g sine theta. So g sine angle of theta, and the t square is 4.5 seconds. So That's 52 meter per second, 4.5 seconds plus half, 9.8 meter per second square times sine angle of 65 times 4.5. So seconds. So that gives you the distance about 294 meters. So this distance, this distance from point A to point B is 294 meters that we just found. Now in the right triangle, the big one, it's 65 degrees and this distance is 294 and we need to find this h. So if you use sine angle of 65, you'll get h over 200. Oh, it's not 294, so I misread my calculations. It's 324. Sorry for that. Here's 324. Sorry for that. And 324. So this is if this is a right triangle and if this side is 324, then what we can guess right now is this distance has to be less than the hypotenuse, right? In a right triangle, the greatest distance is the hypotenuse. That's the opposite to the 90-degree angle. So that is over 324. So that is your h is 324 times sine of 65, that is 324, and that will give you the answer of 294. So I misread h as s in my calculation, and the unit is meter. So do you have any question? Okay, let's go to part C of the problem. And so now you need to find the final velocity with which the car, hits the bottom of the inclined plane. So you have your initial velocity as 52 meters per second, and you don't know the final velocity, and you have the time as 4.5 seconds. So you just need to use the equation of motion, and that is V final is V initial plus the acceleration. Since this is positive acceleration, I'll just write AXT, and PF is initial 52 meters per second plus, the acceleration, that is G sine angle of theta times the T, the acceleration with which the car is going downward, that is G sine theta, and that is 52 meters per second plus G is 9.8 meters per second square. The angle is 65 and the time is 4.5 seconds. So in total, you will get your VF as 92 meters per second. So number D. So now what the problem says is that as soon as you are done with the first inclined plane, the car starts to go to second inclined plane. So there was one inclined plane at the beginning over here, and the car again climbs the another inclined plane, but there aren't any other forces acting on the car, so it's solely depend on the acceleration and the forces that it had when it came down through this inclined plane. So let's suppose that the car can reach the maximum height of this and stops at this height, and the initial velocity at that place was 52 meters per second, right? So now we have the final velocity as 92 meters per second. So here the initial velocity is the final velocity of our last case. That's the initial velocity. Let me write this as initial velocity prime at this point. That is point B. Let's call it C. Point B is 92 meters per second, and the final velocity is 0 meters per second. So you need to find the distance from here to here. So again, let's use the equation of motion, that is V final prime square is equals V initial square plus 2ax delta x prime. Let's call it delta x prime. So here the acceleration will be negative g sine theta. Why? Because last time the car was coming down and the gravity was also in the same direction, but here the car is going up and the acceleration due to gravity towards the x is towards this direction, the x component of the acceleration due to gravity. So we'll use a negative sign. And it makes sense because we want the initial velocity decreased by this minus sign as it goes as it climbs the inclined plane. So this is 0, and you have like the initial velocity. So your delta x prime is v initial square over 2 times ax, and that is minus v square 2 minus the sine angle of theta. Okay, so negative signs cancel out, and 92 meters per second square divided by 2 times 9.8 meters per second square times sine angle of, so it has a different angle. This is a 45-degree inclined plane, so it's, let's call it theta prime 45 degrees. So I need to change the notation here as well. So it's g sine theta prime. So it's 45. So this gives you distance as 610 meters. So I think that's it for today's review session. So if you have any problem, now is the time you can ask me problems. Yeah.
I'm sorry, but can you go back to number 2 and explain like how you like proved the final velocity equals the initial velocity just in the other direction?
Okay.
Like I get it from the picture, but like I don't, you said you have to prove it on the exam and I really would have no idea how to do that.
Okay. So I think this is the problem. So the final velocity, so you have like a projectile and you have the 2 components of your velocity at the beginning, right? You have the x component, you have the y component. And the y component becomes 0 at the maximum height, and it starts to increase. So yeah, I guess you understand what I'm trying to tell, how the velocities change throughout its path, throughout its trajectory. So if you have a projectile like this, so you have a launch angle v0, so you have v0x and v0y at the beginning. So you have a y component, some finite y component, and the x component. And the thing to keep in mind is your x component is always the same. It won't change. The x component will be same here, same here, same here, no matter wherever you are in the projectile motion. So at the point when it hits the ground, the x component is same. So the final x component of the final velocity, if it's the final velocity, and if you can resolve it like this to get the x component of the final velocity, velocity, is always equal to the initial v0x, that is v naught of cosine theta. So it's always the same. But the Vy is going to be the V final Y, the Y component of this final velocity. It's always going to be equal in magnitude, that will with the initial velocity. So the magnitude, so the length, this length and this length will be the equal, but in the opposite direction. And it makes sense, right? Because at first, when we were throwing the ball as a projectile, the projectile goes up. So the y component has to be towards the positive y. But at the point where the ball is hitting the ground, we should have the y component of the net velocity vector towards the negative y. So it has to be the final velocity, the y component of the final velocity should be equal in magnitude, but it should be opposite in the direction of the initial component.
Okay, and like what you just kind of drew up here is how you'd like show your work for that on an exam?
It's better if you can like draw a nice diagram and show the vectors where they are pointing. It's always good to have a level diagram. Yeah.
Okay, so this like diagram up here is like an explanation enough for like VFY equals V equals the okay.
Some sentences, some wording would be good, I guess. And I can show you like how to calculate this one as well, but I don't want to do it because they don't recommend it. Because if you take this time as t half, and if you take this time as another t half, and if let's suppose that we are only taking care of this particular segment of time, then your initial velocity is 0, right? The v, because vy is 0 here, and your final velocity is, if you need to find out, will be the initial velocity 0 and minus z times the t half. And if you find t half, you'll get like this vy somehow equal to like negative v naught sine theta. You'll get if you calculate it.
Okay.
But you don't need to do that. You just need to give reasoning that if there is no air resistance, because if there is air resistance, it's not going to be the projectile like this. The projectile will be something like this. It will come to stop earlier.
Yeah.
So since we are not taking care of the air resistance, the final velocity, the y component of the final velocity will be negative of the y component of the initial velocity. And if you calculate the net velocity will also be the negative of the initial velocity.
Okay. Awesome. Thank you.
Thank you. Any other questions?
For this same problem, I'm just confused how you know when you need to actually calculate it, or if you just need to give the reasoning for why.
So they are just asking what's the like final velocity of the projectile as it hits the ground, right? In the problem, I think the wording is something like that. So if you go to number 2, it's number 3, number 2. So what is the velocity of the ball directly before it lands back on the ground? So it's fine if you can calculate and give numbers, because I think we also have numbers in the problem, but I don't think like you need to put any number over here, because the main important thing about that is that even if you do the calculation, you'll get the same velocity. The magnitude will be the same, the direction will be negative, right? So this reasoning is enough for this problem. But but there could be some problems where you need to calculate the final velocity and so the answer, that x meter per second is the final velocity.
Okay, thank you.
Yeah. Any questions? So if that's it, if there is no other question, then we can end this review session here. And also remember that if you need to ask any other problems, I have my office hours on Wednesday from 3:25 to 4:25. And if you want, if that doesn't work for you, you can email me and we can, set another meeting time. So I wish you best of luck for your exam. And if you have any question, feel free to ask me, email me. Thank you.
Thank you.